systems and start talking about what is an embedded system. So the name embedded comes from the word embed. You have the definitions there, which is to, so it's a transitive verb, so we embed something. And embed means to, as it is written there, to enclose something inside, like fossils embedded in stone, to make something an integral part of some other things, like in the phrase, the prejudice is embedded in our language, or in a more technical perspective, to prepare, in this case, a microscopy specimen for sectioning by infiltrating with and enclosing with a supporting substance. So that's kind of the procedure that when we want to have slices, very thin slices of a cell for analyzing in a microscope, we enclose it in some gel, for instance, that dries and becomes solid, and that allow us to cut very thin slides because it's embedded on this original cell is embedded on that substrate, or to something that surrounds another thing. And so this idea of embedding is the idea behind the embedded systems that we find everywhere. You are all aware today that, for instance, cars have a lot. Today they have a lot of microcontrollers inside. All the engine working, even in fuel engines, is electronically controlled. That's why we can have cars that spend so little gas after 100 kilometers. Why? Because we have sophisticated control algorithms deciding what to do, how much fuel to inject to the engine, depending on the rotations at that moment, on the torque that is required, on the gear shift. So everything is electronically, the working of the engine is electronically controlled in an engine. Airplanes are another example of the application of microcontroller systems. Sometimes with, let's say, with very bad consequences. Perhaps you have heard about the MK's problem in the Boeing, in the Boeing 737 MAX. Did you read that news?
Yes.
I heard about it.
And can anyone just say briefly what was the cause of what caused those problems?
Well, that I don't know.
Does someone knows? Does someone know? Well, the idea was that has the Boeing 737 is an airplane which is about 30 or 40 years old, and during it has there have been several models, and one thing that happened over the time is that the diameter of the engines became much larger. And so what happened was that they had to slightly change the position of the engines in the wing. And by changing that position, all the dynamics of the airplane change. And in some conditions, the airplane had the tendency to lift the front part more than it should do, because the motors were now on the different position. And so the people from Boeing decided to introduce a system that would make some compensations on every airplane setting, on the settings that control the attitude of the airplane, in order to compensate for the tendency for the nose to go up, and it would force the nose to dive, in order to improve the stability of the plane. The problem was that apparently this depended on a single, on the information coming from a single sensor. And if that sensor stopped working correctly, this compensation system would start acting even when it was not necessary. And this going into action when it's not necessary meant that the airplane was driving normally, and suddenly the nose would start diving, would start going down, because of wrong information from the sensor. Well, there are other aspects in this. First, this is a major design flaw. We cannot depend, for such an important thing, we cannot depend on a single sensor. And also, as it was considered that pilots would never have to deal with MCAS, pilots were not trained to deal with it. So it means the first time it occurred, the pilots were not understanding what was happening. And and as a result, 2 planes crashed with everyone inside dying. And we can say with reasonable trust that there were no more crashes, because all those those 737 airplanes were landed, and no more flying was allowed. And this is an example of the importance of embedded systems. So we see here the notion of embedded. You look at an airplane and you don't see the electronics. You don't notice that all these flaps that we see in the figure, the wing flaps and all the landing gears, all that is electronically controlled. There are electronic signals running over the airplane body and sending instruction to this and that, and we can have things in the middle that we don't see, that we don't know that exist, but they are doing their own work. For instance, another example is in cars. Do you know how the ABS works? Anyone? Do you drive? Do you have a driving license? Have you ever experienced the ABS system working?
Yes.
It prevents the wheels from locking.
And how does it do that?
I suppose it lowers the brakes on that wheel.
Yes. Yes. When? What's the condition for?
When the floor is wet or with dust. Does it?
It happens when the floor is wet, but the car doesn't know if the soil is wet.
I suppose when it senses a slippage on the wheel.
When it blocks the wheel. When the wheels
Yeah.
block, the brakes are attenuated or modulated by the anti-block system.
Yeah, that's right. That's the point. When it detects that the wheels are blocked, the brakes are released, either totally or partially. So think about what does this mean. when you're driving a car, you want the brakes, you don't want the brakes to fail, right? Especially if there's a wall in front of you, right? But what is an ABS, an anti-blockage system? An ABS is something that is between the braking pedal and the brakes, and it has the power to decide that you may be pressing the braking pedal as strongly as you can, and that thing in the middle will decide, I won't brake now. So embedded systems in many situations cannot fail. And that's one important thing in embedded systems, that we deal with human lives, as we have seen in this example. In the ABS, in the airplanes, or even directly. Who recalls the Volkswagen scandal?
Yeah.
What was that?
I think there was some about diesel engines, but I guess it's not about this one.
Yeah, I can hear you very.
Oh,
Can you speak louder, please?
I'll try to change my settings. Is it better?
Yes, yes.
I was talking that I think there was something about the diesel engines in the US, but I don't think it's about this one.
Yeah, it's about the.
Oh, it's about this one.
Yeah, but do you know the details of this story? Let's call it.
It was something about the emission.
Yeah.
But I don't really remember all the details about it. I just know that there was some case.
Okay, what happened was that all cars have to undergo testing before going to the road. When you build a new car, you have to submit it to the authorities because you are subject to emission regulations and so on. And what happened in the Volkswagen case? Well, they build the cars, they send it to the authorities, and the authorities make tests. Well, they put the car in a testing system with rollers. The car is rolling on top of those rollers. And then they have sensors, mainly in the exhaust pipe and the other locations, to measure how much particles and nitro oxides and carbon monoxide is going out through the exhaust pipe. And what happened was that Volkswagen announced some levels of emission that were confirmed by the tests from the authorities. But then there was a researcher that found those values a little bit strange. And what it did was install the same sensors in a car, in a Volkswagen, and decided to drive along the roads with that. And what he found was that the values of pollutants emitted by the car were much higher than were announced in the tests. And then he decided to repeat those tests and start talking with other people, and other people confirm those values. Effectively, what was measured by using the car was much higher than was announced in the tests. And they start thinking that the people that made the tests that had not done their job properly. Well, it happens that they have done their job properly. Do you know what was the cause for the different readings?
Yes.
The systems were lowering the performance on purpose.
Yes, the systems were detecting test conditions Because usually how do you do a test? You set the car on the rollers and then you put it to rolling at the same speed for some time. And the software those embedded systems would detect that situation and manage the fuel supply and all the engine working in a way to reduce pollutant emission. But this would reduce the power of the engine too. And if people would drive the car on that condition, they would feel, let's say, a lazy car. And so there was software to detect, am I in tests? Go to lazy mode. Am I on the road? Go to sport mode. Well, if this is not tricking, well, I don't know what other name to call it. And so this was a serious problem because for many years, there is suspicion, Volkswagen was caught on this, but there are suspicion that they are not the only ones, or they were not the only ones doing that. But this means that a lot of cars had been circulating for a lot of years, emitting much more pollutants that they were supposed to. And this also brings the issue of ethics. We see that embedded engineers deal with a lot of, it's not just writing software. We're dealing with machines that deal with people's life and can interfere with their health, or at the extreme point, they may be killed when the embedded systems do not work as they should. That's why we will talk a lot in this course about how to develop good quality software. That's why one of the first things that I mentioned is that we are going to talk about how to develop quality software, because we need to if we want to have our lives protected. Okay, of course, if I'm developing software for a coffee maker, I may be much more relaxed. It's hard to think that it will have major consequences, but even though it may explode, and a container of boiling water to explode is also dangerous. So if you take the road of embedded system development, always think that you need to do things properly, because embedded systems deal a lot with everyone's life. So this is moving forward. This is a text that I will leave in the screen for some time, that I met a few years ago, and I found it curious because it talks a lot about what is to be an embedded systems developer, and what happens when you try to explain what you do. So I will give us just a few minutes for you to read this. Okay, so if you go into embedded system programming, because these systems are hidden inside other things, that's kind of the things that you may run into, having these feelings of finding hard to explain what you do. And so what I would like to do now is, after these reflections on embedded systems, for you to think about what makes a system in sharing now. And I'd like to propose you an exercise. I will split the exercise, allowed you to have a look at what are the difference of between embedded systems and PC-like. And I guess that you all may have found the common features. For instance, like that the systems, embedded systems are purpose specific. PC-likes are more like general purpose systems, and they face PCs are made to work inside homes and on controlled environments, and embedded systems many times work in hard conditions. And so, so I could have here some of the possible answers for that, for the table that I presented you. And I would like to draw your attention to the last line of this table, which is a curious figure about embedded systems development, which is the market share in number of CPUs. And notice that this value is probably outdated, because with the explosion of IoT, and IoT devices are clearly embedded systems. Before IoT, we already had 98% share of CPUs for embedded systems, and only 2% was for PC-like systems. Why? Because currently we can have even our toaster or coffee machine may have a microcontroller inside. So if you ever go for embedded system programming, you have, surely you will have, there will be a job for you. And this is an estimate of the size, market size for embedded systems just for Europe. We are talking about something reaching the 60 billion US dollar. So there's only in Europe, so there's a lot of money involved here. And we can see the larger application areas are automotive, healthcare. Think about all the talk that has been around about intensive care units. Intensive care units are embedded systems everywhere. That's another huge application of embedded systems. Then we have the area of consumer in electronics, again, toasters and washing machines and TV sets, and all those things. And finally, a significant amount for military and aerospace. So this gives you an overview of what embedded systems are. So notice that we have talked about, we are in an engineering degree, so we must always consider that we are developing things for society and for people individually to use. And we always must take care of that. And finally, that embedded system is an application domain, and that will also helps to contextualize many things that we will talk about in this embedded system module, which is that practices are relevant. It's not only what we do, it's how we do it. We will talk about developing processes for embedded systems. Why? Because embedded systems is engineering, and engineering work occurs in teams. We don't work alone. We work with other people, either people that do jobs different from our own. We must work with mechanical engineers, with designers, and so a lot of other professions working in the same team. And teams have several embedded system programmers. So we must have a development process that allow us to create some work, store it somewhere, and make it in a way that the next person that works on that software that we have development knows clearly what to do and starts working the moment it gets the software in his hands. And so this has a lot to do with our practices, with how we do things. And I leave you here with some links about what I would call tools of the trade, which are online magazines and journals which are dedicated to embedded systems. EE Times and EE Times is more generalist, but with a great focus on embedded systems, and embedded.com is clearly on embedded systems. And you have companies like those in the bottom, the Bar Group or Gensel Group, which are people that have, usually they are the company created by some person. In first case is a guy called Bar, and the second one is by Jack Gensel. And they have a lot of information about embedded systems. They have newsletters that you can subscribe and get information that will allow you to, right now, as an embedded in systems student, to understand what are the major concerns in embedded systems. And later on, when you are working professionally, if you decide to go on for embedded systems development, to be constantly updated on your practices.